Hi, everybody. As Sabrina said, I am a lecturer and researcher at the Transylvania University of Brasov. And I also... And I also work for Intech Engineering Services in Brasov. Considering it's the wrap-up session, I'll try to be as concise and informative as possible for you guys that stayed here till the end. The subject of this topic pertains to the wider scope of homomorphic encryption. I don't know how many of you are familiar with the subject. Okay, I'm glad that we have here people that know about it, and for the other ones, it will be an informative presentation. I'll start with a little bit of history, briefly. As you all know, the encryption systems are divided into two main groups: symmetric encryption and asymmetric encryption. The symmetric encryption has the feature that the encryption and the decryption processes can be done with the same key. And one of the most well-known examples is Caesar's cipher, which is based on a simple transposition of the bits that compose the message. I won't insist too much on this. And obviously, this poses real security problems, as by just learning what the encryption key is, we could also decrypt the message. And a few examples that were somehow well known in the history are the Vigenère code and the famous Enigma encryption machine that was used by Germany in the 30s and during the early 40s, till the end of the Second World War. The decryption of the messages that were created by Enigma started in the early 30s and was accomplished first by Polish cryptographers, and those for political reasons that I don't comment here, and the knowledge which the Polish cryptographers acquired was passed over to Bletchley Park, so to the British cryptographers, which carried on the work with relevant success during the war. The second category of encryption systems is based on the asymmetric encryption systems, which have the feature that the encryption of the message is performed by a public key at the source of the message, and the deciphering of the message is carried over at the destination using the so-called private key. We'll see in an instance why this kind of asymmetric encryption is particularly important for homomorphic encryption. obviously, any website which uses SSL encryption is based on this very principle that I have just asserted. For example, when you have a form that allows one to authenticate, the encryption of the username, password, and any other data is done at the source using the public certificate, which the browser sees. And then the server, as soon as it receives the encrypted message, will use the private key which is stored on that server in order to decrypt the message. This is the general form of the RSA encryption system, which basically, as we'll see in an instant, was the theoretical construct which the creators of homomorphic encryption took into consideration. Basically, the upper row is taking into account a plain text message, plain text as in unencrypted, and it also considers some large numbers, E, N, and D. And the second row performs the reverse operation over the encrypted message C, and using the modulo operation. But at that time, the problem is that what people could do with encryption was only encrypt the messages and then decrypt them. There was no possibility to perform any lucrative processing over that data. This is why the idea of homomorphic encryption appeared as a concept. Actually, as a concept, homomorphic encryption exists for several decades, but as it was too computationally expensive, it hasn't become possible in practice until recently. So we could see an incipient way of talking about homomorphic encryption. For example, when we send data from a mobile device, this data could be sent over to a server, which is able to compute somehow this data, and then it will return back the results to the requesting mobile device in this example. The problem is that the processing on the server can be made either over the plain text data or using the encrypted form. But in the context of the standard RSA systems, RSA-based systems, it is not possible to carry over computations over encrypted data. So basically, this is the main idea of homomorphic encryption, allowing programmers to design and implement computations directly over the encrypted data, and even returning them to the requesting client in the encrypted form, where they can be decrypted for the user to see them. So the need for privacy is obviously the driving force here. Why was I saying that RSA is somehow the original or conceptual foundation for homomorphic encryption? Because as researchers in the field discovered, it is enough to be able for an encryption system to carry over additions and multiplications in order for any calculation to be carried over the encrypted data. And it's very similar conceptually with what the original RSA model tells us. So here we can speak about multiplicative homomorphism, and also we can speak about additive homomorphism. The problem was that standard RSA was generally perceived as a more multiplicative system, while other encryption were more additive than multiplicative. Here we can speak about the two main operations that I mentioned. For those of you that are not familiar with these symbols, in computer architecture, these are called logic gates, and are usually employed in order to design the circuits which make up a computer system. For example, the exclusive OR is represented by this kind of logic gate, while AND is represented by this kind of logic gate. And they have the Boolean algebra significance that you all know, I'm sure. And as Boolean algebra operators, exclusive OR corresponds to the sum operation, and at the end corresponds to the product. Okay. And using this kind of these basic two operations, we can perform any computation of any complexity over encrypted data. So fully homomorphic encryption means that the specific encryption model supports both additions and multiplications. It has been researchers in the field have continuously looked for a feasible solution to this problem until in 2008 Gentry, for his PhD thesis, proposed a viable system. And his system was able to basically perform any kind of basic operation using additions and multiplications over the encrypted data. But unfortunately, at that time, the execution time was quite high, as the system was in its early stages. So, as a general as a general principle, we can speak about choosing the secret key in the form of a very large odd number, and then we can compute the ciphertext using this general form. The last part of this formula is known in the field of homomorphic encryption as noise. Why is noise so important? First, we cannot live without the noise, because otherwise the text would be dangerously easy to decrypt. But if the size of the noise is greater than half of the encryption key, then the decryption will produce incorrect results. So, arrived at this stage with our presentation, I can say that one of the most important checks and balances when working with homomorphic encryption pertains to finding the right balance between the size of the noise and the size of the execution time, which that particular method produces. We'll see the use case, and I'll show you some real execution times which I obtained, and you'll see that they are not negligible. They can be quite high. So what is the method that allows us to keep the noise at an acceptable level? Gentry and his fellow researchers called it the bootstrapping method. Basically, bootstrapping means that starting with a certain level of the noise, we think about the maximum possible level of this noise, which relates to half of the size of the encryption key, and then we implement in our code, which defines the homomorphic encryption routines, the mechanisms, the logic that would keep our noise at the maximum possible level. In the worst case, of course. If it's less, even less, it's better. So there are various recipes to implement this bootstrapping, and it is one of the aspects of homomorphic encryption which researchers can modify and optimize during their work. So it cannot have a universal form. Oh, okay. So in the early days of homomorphic encryption, even standard non-homomorphic encryption was producing important execution times even for the most basic operations. This is a well-known graph which which pertains to atomic operations. And in 2009, considering the implementation and the power of the computation platforms at that time, we could even wait for 1,000 seconds for basic operations to be carried on. So, as I said, both basic operations in a homomorphic encryption system increase noise. So each time a multiplication or an addition is performed, the noise increases. The multiplication contributes to the increase of the noise in a more drastic fashion, as it squares the actual value of the noise. So the goal is to do noise reduction, but the researchers is presented with a dilemma in this case. If I want to reduce noise in its entirety, I may obtain a direct decryption of the message. So I may give over all the secrets that I'm trying to protect, which is not what I want. So we speak here about circular encryption and decryption mechanism, which basically involves an intermediate step that allows us to include in the discussion, in the model, the bootstrapping and the proper management of the noise's value. Okay, so this is the main idea, and the model is called circular encryption, as I have I have already mentioned. And another mention for those of you who are not familiar with the concept of homomorphic encryption. Those who design such a system usually refer to the encryption circuit. Encryption circuit is used with the very significant which we may think of. I mean the circuit, the physical circuit of the computer, of the server, which carries over the homomorphic encryption operations. And very often when a scheme is designed, they also write down the architecture of the computer system, which carries over the computations with all the logic gates that are involved in this process. So the circuit is not just a metaphor. Okay. So I'm quite close to the case study that I wanted to present today. One of the last theoretical mentions that I would like to make pertain to the size of the noise. So when we use this circular encryption system, we have a noise considering the input data that flows into the system, and we have probably another size of the noise for the data which is found at the output of the system. And regardless of the size of the input noise data, the output is always fixed, and the optimal value for this fixed size is determined through sequential iterations of the development process. Okay, so just not to bug you more with this, it is very important that you retain in your mind the principle of bootstrapping and the fact that the noise cannot go over a certain threshold. And one of the other Gentry's remarks refers to the fact that if an encryption scheme can evaluate or his own decryption model, decryption circuit, then it can do any other task or mathematical operation that he is being fed with. Starting from these basic concepts, I have implemented in a joint work with IBM Romania from Brașov system which basically considers and implements these principles. The architecture of the system is fairly simple. The end users is featured with certain sensors which monitor their biological parameters. For example, in our study, we have used devices for the heart rate, and these devices were connected to the mobile devices, mobile phones, which at their turn were using the data connection to transfer the collected data to the processing backend. We have also proposed here two data paths. Why two? Because, as we'll see in an instant, homomorphic encryption is by definition, it still is, a very computationally expensive operation. Essentially because in the background it uses those multiplication and additions that I mentioned. And when we just collect the data, we use this upper data path that only considers a standard AES encryption model, because it is obviously more efficient from a computationally perspective. So it wouldn't be justified to use encryption from the first instance. And the fully homomorphic encryption path, so the bottom one, which is represented in this figure, is only relevant when the user from his client application requires some data for the backend. For example, he may require to the application to estimate if he or she is susceptible to have a certain cardiac condition. And this data may pose obvious security and privacy concerns, because it wouldn't be nice for an intruder that is staying somewhere in the middle to learn that a certain person is is concerned with a disease. So, sorry. Here, the user sends the request to the processing backend. The request goes through a homomorphic encryption process, and the data is properly packed. It gets to the backend here, which for our use case is stored in IBM's Bluemix platform, but this is not relevant. It can be stored in any other cloud infrastructure which supports this kind of deployment. And the background essentially performs the computations directly over the encrypted data using the additions and the multiplications that I mentioned in the previous slides. And the results are being fetched also in the encrypted form and sent back to the client device, which knows how to decrypt them and will offer the results to the client, to the requesting client. There are two main advantages in this scenario. First, the communication channel between the client which requests something up through the server that performs the computations is secured. The data is not sent in plain text. And the second significant advantage of this model is represented by the fact that the computations are not carried over plain data, but directly over encrypted data. Why is this important? Let's think about the recent CPU vulnerabilities that we were made aware of at the beginning of this year, Spectre and Meltdown. And these have particularly affected the systems of important cloud service providers. And this essentially means, without going into too much details, that an attacker, regardless of the security measures which are implemented on the nodes that make up the cloud infrastructure, can simply access the data on the server by using these flows that exist in Intel CPUs. So all the Intel CPUs that are manufactured from 1995 till today, I think, are flowed by this vulnerability. And if the data, this medical data, was processed in an unencrypted form, it is very likely that an attacker, a very talented attacker, could access the medical data that is stored in a cloud infrastructure. So if the application, the system that one wants to deploy does not use the company's servers and uses a third-party infrastructure, then this is a potential solution for the privacy concerns. So the model that we have implemented basically support 4 kinds of operations. The first 2 of them, as you would expect, basically refer to the addition and the multiplication, which form the basis of this model. And then the rotate and the select are in principle concerned with maintaining the noise at an acceptable level. So without going into too much detail at this stage, I can tell you that this homomorphic rotation is essentially allows one to rotate the bits of the data that is being processed in order to keep the noise at an acceptable level, while the homomorphic selection has the role to correct the potentially affected altered slots that may appear during the multiplication and addition operations. Let us recall that if sometime during the processing the noise goes over the level that I mentioned, it is possible that the result of the operation will be flawed by inconsistencies. What would this mean? For example, for this medical system that I am discussing about, this would produce an incorrect diagnostic, or it could simply make impossible for the result to be mapped to the correct patient, which is obviously a very important problem. So how it was the bootstrapping implemented? In our case, the bootstrapping was implemented using a parameter that is called level. The level increases each time a multiplication or an addition is carried over the encrypted text. And inside the code, we have specified the necessary logic for this to be kept at an optimal level. And this allows for the most expensive multiplication operations to be conducted without compromising the integrity of the returned results. Considering that I've spoken about the homomorphic encryption circuit, it is a very raw example of how such a circuit could look like. We can speak here about the actual application of the homomorphic encryption routines over the input data, and here on the bottom level we could speak about the bitwise operations that are applied on the encrypted data. Considering the operations that I mentioned, obviously the most important are the additions and the multiplications, and then the other ones have the role to keep the noise at an acceptable level. I spoke about the fact that this homomorphic encryption system is very computationally expensive. And we have made some tests which give us an idea about how computationally expensive is. Basically, we have considered three medical conditions for the prototype that we implemented. It's the average. It's the average heart rate, the delayed repolarization of the heart, and the minimum and maximum heart rates. This delayed repolarization of the heart is a medical condition which appears right inside the heart muscle, and it basically means that some incorrect voltages that are applied to the nervous terminations of the heart muscles determine the valves not to close correctly, and this may lead to sudden death of the affected patient. And the principle, the physical architecture of the system is simple. The heart rate data has been collected. It has been transmitted over to the backend. And when the user wants to know if the collected data may suggest that, for example, the delayed repolarization of the heart is possible, then a request is being sent to the server, to the backend. And the backend carries over the computations using the homomorphic encryption model and returns the results in encrypted form to the user, such that he or she is able to obtain an opinion. And regarding the parameters that we used during the performance assessment. NCT refers to the number of the ciphertexts that have been successfully created during the process. The level is the value of the level, that parameter which allows us to keep track of the noise and maintain it at the optimal level. XFR is a jargon from networking, which basically means transfer. And it's transfer in and transfer out. Transfer in means the data which the processing backend receives from outside, and transfer out is the data which it supplies as answers to the requesting clients. Transfer out may be relevant, especially relevant when the system is hosted with providers that bill considering the quantity of the data that is being transferred and uploaded. Usually the uploaded data is taken into account. And here, storage ratio refers to the quantity of disk space that is necessary to store one byte of plain text data. It is good to keep in mind that for 1 byte of plain text data, we'll usually have more bytes of encrypted data that will allow us to homomorphically process it. This is one of the other problems which should be taken into account. And PS is simply the parameter of the process speed, which tells us how fast the data is processed inside the system, the backend. And we can see here that for a 1 minute run, for an interval that involves readings every minute, the amount of the transfer data is almost 3 terabytes, and the value of the level L is 12. So the algorithm somehow managed to keep it at this level. And for example, for readings that involves daily updates of the data, the system generated more than 2,000 ciphertexts, and the value of the level that was observed was higher. So you can see that the method requires quite a lot of computational resources, and this is not necessarily bad for researchers, because those who may be interested in working in these directions and on improving the homomorphic encryption system may have a lot of space to express themselves and properly contribute to the field. And these are the same performance metrics which were recorded by a performance test in connection to the delayed repolarization syndrome. Again, we see here that there are important values for the parameters that are involved. As a general conclusion to this, by working directly and by researching on this topic for almost 3 years now, we have determined that this kind of homomorphic processing of the data is indeed very helpful in order to address the privacy concerns that arise nowadays. But we are far from arriving at the optimal solution, because the execution times and in general the computational resources which are required to perform this kind of computation are important. So if you will ever be interested in working in this area, you'll certainly have a good deal of space to express yourself in the foreseeable future. In principle, this is the presentation. Now, if you have questions.
Thank you very much, and we'll be taking the last questions for today and for this event. Let's start in an orderly manner. We'll start from here and go throughout the room.
Hello.
Hi.
So the homomorphics are used to preserve the data from the encryption. Wouldn't for the noise, if we use values less than 0 to be convergent, would it affect the data, or because this way it wouldn't be needed to limit the value of p?
So you basically ask why we refer to bits of 0 and 1, or I didn't fully get your question.
I was referring about the noise function.
Okay.
Because of the multiplication, it would get very big.
Yeah.
And it would affect the data.
Yeah.
If the function were convergent, it would affect the data.
If so, basically the data, in plain words, the integrity of the data would be affected only when the noise is too large. So the fact that we mentioned there specifically bits of 0 and 1 simply means that we work directly with the computer system's way of understanding the data that it receives. So this is why we think about zeros and ones when designing the system. And to specifically answer your question, the integrity of the data that is being obtained after the homomorphic processing is only affected in principle when the noise is too large. So we haven't, in practice, we haven't found any other scenario that would involve altering the data in a way that it would make it impossible to associate with a patient or somehow else.
Thank you.
Thank you. Raise your hand too. We'll just take it gradually.
Hi. I'd like to know, I mean, you have what
If you
seems...
can keep the microphone a bit closer.
What looks to be a concrete example from you here. At what point will you see this commercially available, where you can actually create or, use this to process client information, medical health records in the cloud, and at process rates that are usable in a commercial context? Actually,
we used our prototype in a concrete setting in Brasov, and we have basically offered the medical sensors to a batch of let's call them patients, although not all of them are patients in the proper sense of the word. And the system is functional, is viable, but we think that it is still not suitable for very large settings. So it will be commercially available if someone has the desire to invest money into this kind of a system, when it will be sufficiently optimized so that the execution times will become lower than they are at present. So, in my opinion, this is the main bottleneck at the moment.
Thanks.
Thank you. We will have 2 more questions in this section, and then we'll move to that slot, okay? We have there a person.
I'd like to ask, where does the noise come in the first place? If I recall correctly, noise noise is squared every homomorphic rotation. If we work with plain text and 10 homomorphic encrypt days, we should begin with 0 noise. If it's squared, where it comes from, it has to be setted.
So the noise basically comes from the successive application of the 2 functions, the multiplications and the additions. Even for basic operations, it may be possible for successive usages of these functions to be necessary in order to solve those particular requests from the clients, and therefore the noise may increase quite rapidly, and if it is not managed properly, we may have the impression that we obtained the result. We will send them back to the client, but upon decryption, he'll get meaningless.
Thank you.
So addition and multiplication are the two keywords when speaking about noise increase.
Thank you. We have a question in the second row, right here.
Hello. First of all, thank you for your presentation. So this is a scheme for encryption database query, if I understand correctly. Is that right?
In this case, yeah, there are not necessary database queries, although it can be perceived like queries in the database. Yeah, we have a database in the backend. So in order to simplify things, yeah, you may say that it's a database query, yeah.
I was curious if fully homomorphic encryption can be coupled with elliptic curve cryptography in some sense. Maybe you research this more carefully.
It can be coupled, but in principle, yes. As a concept, it can certainly be coupled with this kind of encryption. But for a practical setting, we may weigh carefully the advantages and the disadvantages of this, as coupling it with this kind of encryption may increase also the complexity of the processing model, which may further affect the processing times. So we haven't conducted concrete tests regarding the execution times in this kind of a scenario, but it may be interesting to do something like this, yeah.
Thank you again.
Thanks.
Thank you. To the first row there, and then to you guys.
Thank you. I just wanted to ask, have any companies tried to take this to the next step, the scheme?
I'm not aware of a company which is commercially striving to bring on the market such a system. But I am convinced that research efforts are being put into this. And the delay of the market availability of such a system only pertain to the leftovers of the suboptimal behavior of the system. For example, IBM Brashov was keen on working on such a research topic. But again, commercially, it's not available to my knowledge.
Thank you.
Thank you. And the last two questions there.
Hi. Considering how the industry is very, very interested in our private data, do you expect more big companies to support the research in this domain in the near future?
I would expect, yes. If you ask me about how I see the future, considering the fact that it is increasingly necessary to ensure as optimal as possible privacy of the data, I would expect that a more important amount of resources may be invested into this. So, yeah.
Thank you.
Okay, my question is about the operation that we are using with the homomorphic encryptions. I mean, are we like limited with only adding and multiplying? Can we do like comparisons and other different operations? Like, I don't know, but it seems reasonable that we should do something more like.
So you mean if we can do some other operations apart from...
From those that you talked about, like multiplying and those, I don't know.
Specifically speaking about homomorphic encryption, the main idea of the system is that only these two operations are necessary. And these two basic operations are necessary, and they are by themselves quite expensive from a computational perspective. So I would say that at least considering my perspective on the field at this moment, that we shouldn't think about something else than multiplication and addition.
Thank you.
You're welcome.